The comforting lie we tell ourselves is a story most of us grow up with, that Earth is ordinary, not special, not rare, just one planet among countless others, orbiting a typical star in a typical galaxy. It's a reassuring idea. If Earth is normal, then the universe should be full of similar worlds. If similar worlds are common, then life should be everywhere. And if life is everywhere, then we don't feel so alone. But notice something important. This belief didn't come from evidence. It came from expectation. For almost all of human history, we had exactly one example of a living planet one. And from that single data point, we quietly assumed it represented the average. That assumption felt reasonable, not because it was proven, but because it was emotionally convenient. Modern astronomy was supposed to test that idea. We built powerful telescopes, we scanned the sky, we found planets around other stars, thousands of them, and instead of confirming that Earth is typical, the data did something uncomfortable. It began to erode the assumption itself, because the more planets we discovered, the less familiar the universe started to look. Worlds larger than Earth, but smaller than Neptune, planets hugging their stars in tight, unstable orbits, systems wildly different from our own. The expectation was familiarity. The result was strangeness. At first, it was easy to dismiss this as a bias. We told ourselves we were only seeing the easy-to-detect planets, the big ones, the close ones. Earth-like planets, we said, would come later. But even as our instruments improved, the pattern didn't disappear. The universe wasn't rushing to show us copies of home. Instead, it kept showing us how unusual our setup might be. And here's the part that often goes unspoken. We don't assume Earth is typical because science demands it. We assume it because the alternative is unsettling. If Earth is not average, if our planet is an outlier, then the conditions that allowed us to exist may not repeat easily. That doesn't mean life is impossible elsewhere, but it does mean we can't casually assume it's common. Science doesn't start with comfort, it starts with honesty, and the honest starting point is this. We do not yet know whether Earth is typical or rare, but the evidence we do have is quietly pushing in one direction, not toward familiarity, toward exception. Which raises a question most people don't like to sit with. If Earth isn't normal, then what exactly made it work? And how many chances did the universe really get to try? The planet types we never expected. When astronomers first started finding planets around other stars, there was a quiet confidence in the background. We thought we knew what we were going to see. Rocky worlds like Earth, gas giants like Jupiter, orderly systems spaced out the way ours is. After all, our solar system was the only example we had. It felt reasonable to assume it was representative. Then the discoveries started coming in, and almost immediately, things went wrong. The first planets we found weren't gentle Earth, like worlds at all. They were massive, scorching giants orbiting incredibly close to their stars, planets that shouldn't exist, at least according to what we thought we knew. At first, this was blamed on detection limits. Big planets are easier to see, close planets are easier to find. So again, we told ourselves this is just the beginning, but as the numbers grew into the hundreds, then the thousands, a pattern emerged that could no longer be ignored. The most common type of planet in the galaxy is one we don't have. Super-Earth's worlds, larger than Earth, but smaller than Neptune. Too big to be purely rocky, too small to be gas giants. Dense, massive, often packed close to their stars in tight orbits. Statistically speaking, these planets are everywhere, and yet our solar system contains none. That alone makes Earth unusual. Not because it's perfect, but because it belongs to a class of planets that seems underrepresented. Earth isn't sitting at the center of the distribution, it's off to the side. Now consider what that implies. If the most common planets are nothing like Earth, then Earth-like may already be a misleading category. We're not comparing Earth to the average planet, we're comparing it to a minority, and it gets more uncomfortable. Super-Earths don't just differ in size. Their gravity is stronger, their atmospheres behave differently, their geology evolves on different timelines. Conditions that seem trivial on Earth, like plate tectonics, stable oceans, or a breathable atmosphere, may not arise naturally on these worlds at all. That doesn't mean they're lifeless, but it does mean they're not familiar, which quietly undermines a popular idea. That once you find a rocky planet in the right temperature zone, life is almost inevitable. The universe doesn't appear to favor Earth-sized planets in Earth. Like orbits, it favors something else. And our planet missed that trend entirely. You can still argue that Earth-like planets exist. They do. But exists is not the same as common from a scientific perspective. Rarity matters. If Earth sits in the tail of the distribution, not at the peak, then life may be tied to uncommon planetary conditions, not miraculous, just unlikely. This doesn't mean the universe is hostile, it means it's indifferent. It produces many outcomes. Most don't look like home. And here's the deeper implication. If Earth is already unusual at the level of basic planetary architecture, then every additional requirement for life compounds that rarity Before we even talk about biology, chemistry, or intelligence, Earth is already asking the universe for something it doesn't usually give, and that should make us pause, because the universe has no obligation to repeat itself. A star that's too quiet. Earth's story doesn't begin with the planet itself. It begins with the star it orbits. When we imagine stars, we picture them as steady sources of light and warmth, reliable, predictable, almost gentle. But that image is misleading. Most stars are not calm. They flare. They erupt. They blast their planets with radiation and charged particles. Young stars are especially violent, stripping atmospheres, boiling oceans, and sterilizing surfaces long before life has a chance to stabilize. Or Sunday is different. It is unusually quiet. Not completely inactive, but stable enough to allow a delicate balance to persist for billions of years. That stability is easy to take for granted because it's all we've ever known. But when astronomers began studying other stars closely, they found that solar-like calmness may not be the default. Many stars flicker erratically. Some unleash powerful flares without warning. Others vary in brightness enough to destabilize planetary climates. Even small changes matter. Life doesn't need perfection, but it does need consistency. A planet can adapt to slow change. It cannot adapt to chaos. A star that's too active can erase progress faster than evolution can build it, which means habitability isn't just about distance, it's about temperament. Earth sits in a narrow zone around a star that behaves itself, and that zone isn't guaranteed. Even more unsettling is the timing. Stars change as they age. They brighten, they slow, they become more or less volatile. Earth didn't just need the right star, it needed the right star at the right time, too early, and the young Sunday's activity could have stripped Earth's atmosphere too late, and increasing luminosity would destabilize the climate. Earth exists in a long, stable middle period, a window that may not last forever, and that raises an uncomfortable possibility. We often talk about habitable zones as if they're static rings around stars, but in reality, they drift, they evolve, they move. A planet doesn't just need to be in the right place. It needs to stay there long enough for complexity to emerge. That requires patience from the star, patience from the system, and patience from the universe. Now consider this alongside what we've already seen. Earth is not a typical planet. Its solar system doesn't match the most common architecture, and its star is calmer than many. None of these factors alone forbid life, but together they narrow the path. Each requirement reduces the number of worlds that qualify, not to zero, but not to everywhere either. The more we learn about stars, the more it becomes clear that habitability is not just a matter of physics. It's a matter of timing, stability, and restraint. And restraint is not something the universe is known for, which leads to the next realization. Even a quiet star isn't enough, because Earth isn't protected by a single lucky condition. It's protected by a chain of them. And that chain only holds if every link remains intact. The shield we forget about, even with a stable star and a rare planetary type, Earth would still be exposed because space is not empty. It's filled with radiation, charged particles, and high-energy debris moving at lethal speeds. Left unprotected, a planet's surface can be slowly sterilized, not in a dramatic instant, but through constant erosion of atmosphere and chemistry. Earth survives this because it has a shield, a magnetic field. Generated deep inside the planet by the motion of molten iron in its core, Earth's magnetic field deflects much of the solar wind, the steady stream of charged particles flowing outward from the Sunday. Without it, our atmosphere would be stripped away over time. We know this because we've seen it happen. Mars likely once had rivers, lakes, and a thicker atmosphere, but its magnetic field faded. And once it did, the solar wind went to work, the air thinned, the water disappeared, the surface became hostile. Earth avoided that fate, not by chance alone, but by maintaining an active, churning core for billions of years. That requires very specific conditions: enough heat to keep the core molten, the right size to retain that heat without cooling too quickly, the right composition to allow convection, too small, and the planet freezes internally. Too large, and the dynamics change entirely. Again, Earth sits in a narrow window, but the magnetic field does more than protect the atmosphere. It stabilizes climate, it reduces radiation at the surface, it protects complex chemistry, especially the fragile molecules life depends on. Without it, even a planet in the habitable zone could be uninhabitable in practice. And here's where things get even stranger. Earth's magnetic field isn't constant. It fluctuates. It weakens. It even flips polarity. Yet through all of this, it has remained strong enough for long enough to do its job. Not perfect, just sufficient, which raises a deeper question. How many planets lose their magnetic fields early? How many never develop one at all? How many exist briefly in a habitable state, only to lose it before life can gain a foothold? We don't yet know, but we do know that magnetic fields are not guaranteed. They are emergent properties of planetary interiors, and planetary interiors vary widely. So when we list Earth's conditions, the list keeps growing. A rare planet size, an unusually calm star, a long-lived magnetic shield. None of these are impossible, but none are universal, and each one reduces the odds. Which leads to a sobering realization. Habitability is not a single filter, it's a sequence, and failure at any step erases everything that came before. Earth didn't just pass one test, it passed many, quietly, over immense spans of time, and the universe didn't need to offer those chances. It just did once, at least. The coincidence stack by now. A pattern should feel impossible to ignore. Earth isn't unusual because of one miraculous feature. It's unusual because of how many independent conditions quietly line up. A planet of the right size, rare compared to the dominant super-Earth. A stable orbit, not too eccentric, not easily disturbed. A calm, long-lived star, active enough to power climate, quiet enough not to erase it. A magnetic field, persistent, resilient, and protective. A location that remains temperate for billions of years, not just briefly. Each of these could plausibly occur on its own, but they didn't occur on their own. They occurred together, and not simultaneously, sequentially, over time, without breaking. This is what David Kipping often emphasizes when discussing habitability. The problem isn't whether life is possible. The problem is whether life can persist. Short-lived habitable conditions don't matter. Temporary oceans don't matter. Momentary chemical complexity doesn't matter. Life needs time, a lot of it. On Earth, it took nearly 4 billion years for intelligent observers to appear. That's an uncomfortably long dependency chain. Any disruption along the way, a destabilized orbit, a lost atmosphere, a violent star phase, and the story resets, not ends, resets. Back to chemistry, back to chance, which reframes a common assumption. We often imagine the universe as trying to produce life, but the universe doesn't try. It experiments. Most experiments don't run long enough. Earth is one that did, not because it was favored, but because nothing catastrophic happened at the wrong time. That distinction matters because it means Earth's rarity isn't about fine-tuning in the mystical sense. It's about survival through attrition. A planet doesn't need perfect conditions. It needs uninterrupted conditions, and interruptions are common. Impacts, stellar outbursts, orbital chaos, internal cooling. Any one of these can quietly erase progress. Earth has been hit, frozen, heated, shaken, but never fatally, just barely. And that barely is the point. When we look outward and wonder why the universe seems silent, why we don't see obvious signs of life everywhere, this framework offers a sobering answer. Not that life is impossible, but that long, stable stories are rare. The universe may be full of beginnings, but endings come easily. Continuity does not. Earth isn't special because it was designed to host us. It's special because it endured, and endurance is not guaranteed by physics, only permitted by it. Which leaves us with a quieter, more humbling conclusion. If Earth is unusual, then life like ours may not be the cosmic default. Not lonely, just uncommon. And that makes this planet, this fragile, temporary alignment of conditions, far more precious than we usually admit. Not because it's the center of the universe, but because it's one of the few places where the universe didn't interrupt itself.